Hello, everybody. Welcome to another live stream of Chemistry 222. I'm a little late today. I'm a lot late today. My internet went down just before this stream, and it's taken about an hour or so to get it back up. But we're back online now, and definitely there'll be a video posted on YouTube later today about this as well. So let's get started. Today we're going to talk about equilibrium constants, Le Chatelier's principle, equilibrium calculations like the Rice tables and stuff like that, and work through a bunch of problems from the textbook on that regard. So let's go ahead and jump into it and get started. The first problem I'm going to look at here is number 18 out of the textbook. I'm going to do parts A, C, and E just to save a little bit of time on these. And on these, we're given the initial concentrations or pressures of the reactants and products, and are given for each of the following systems. So there's three systems there, A, E, and C. Calculate the reaction quotient and determine the direction in which each system has to proceed to reach equilibrium. So, as you know, equilibriums are basically when the rate of the forward reaction is equal to the rate of the backwards reaction. So both reactions are constantly happening, but they happen at the same rate at equilibrium, so we don't get any change in concentration. And we can calculate the reaction quotient, so in this case QC, would be equal to the concentration of the products divided by the concentration of the reactants. That's the general idea of what we're going to look at. And that's going to be equal to, and at equilibrium, this is equal to Kc. So if we're not at equilibrium, Q varies a little bit. So if we, let's just set a few ground rules here. If QC is less than K, the reaction is still moving to the right. We have more reactants than products, and we haven't reached that equilibrium point. So I'll just say moves towards the right. And we can see that kind of in the calculation where if the QC is going to be less than K, that means that the concentration of the products is not big enough, essentially, or the reactants is too big. So as the reactants goes, the concentration of the reactants goes down, the concentration of the products should go up, and we're going to reach K, and that equilibrium constant or quotient is going to get larger and eventually reach K. If QC is greater than K, well, that means the reaction is really going to be moving towards the left, which means essentially we started out with too much product in there and we're shifting it back towards the right, so we get that equilibrium concentration going. Because if we can see that in the math, the concentration of the products is now too big in relationship to the concentration of the reactants, which is too small, creating a larger number than Kc. If they're equal, and these should all be, then we are at equilibrium. So we're going to run through these types of equations for all of these three different systems and compare it to the K values that they give us here. K, K, and K. So let's get started with the first one. For part A, 2NH3, it's ammonia gas. It's going to be in equilibrium with N2 gas plus 3H2 gas. So if we have this quotient is going to be equal to the concentration of N2 times the concentration of H2 to the third power. And we know that because this stoichiometric coefficient is 3. So we have to take that concentration to the third power, because we're really multiplying it times the concentration of H2 3 times. And we're going to divide that by the concentration of ammonia, NH3, and we're going to square that because there's a coefficient of 2 over there. So this, and they give us values for these, here, here, and here. We can just plug in those values into this, and we get 0.15 times 0.12 squared, or to the third power this is, divided by 0.50 squared. Let's just put that into my calculator. 0.15 times 0.12 squared. Oops, again, that's to the third power. Divided by 0.5 squared. And I'm getting here 1.03, I'll say 7 times 10 to the negative 3. So that's a pretty small number, especially when our KC value is 17. So we can see that in this case, QC is less than KC, which means we're going to be moving towards the right. Moving towards the product side of things. We're creating more product in this case. Looking at part B, part C, I'm skipping around here. We're looking at 2SO3 gas is in equilibrium with 2SO2 gas plus O2 gas. So in this case, we have our equilibrium constant and we have our concentrations. So QC is going to be equal to the concentration of the products. That's SO2 squared times O2. We're going to divide that by SO3 squared. So that's going to be equal to, we're taking our concentrations that are given. It's 2 molar each. So this is really 2.00 squared times 2.00 divided by 2.00 squared. Mathematically, we can see that this and this is just going to cancel, leaving us with 2. So this has a value of 2.00. Comparing that to the 0.23 value for our constant, we're going to see that this is actually going to be greater than our KC, which means it's towards, there's an O in there, towards the left. I don't know why I put a T there. So our quotient is higher than our concentration by quite a considerable bit. So we can see that we need to go back and make more reactants to this. We need to lower this quotient value. And to do that, we need the denominator to be bigger and the numerator to be smaller. And that's going to happen in a certain proportion until we get to that constant value. For part E, see, we have 2NO gas plus Cl2 gas. It's chlorine gas. It's in equilibrium with 2NOCl, which is also a gas. So our quotient here, and here we're looking at pressures. Just to give us a Kp value and pressures. So Qp is going to equal the pressure of NOCl squared divided by the pressure of NO squared times the pressure of Cl2 to the first power. And the pressures they give for this, NO gas is 1 atmosphere, CO2 gas is 1 atmosphere, and NOCl is 0 atmospheres. So there's no product just yet. This reaction really hasn't started. So we don't even have to do the math to know this is going to move towards the right. But just to put that in mathematically, if this is 0 squared divided by 1 squared times 1 atmosphere of each of those at the bottom, we can see that this is a K value of 0, or sorry, a QP value of 0, which is going to be less than K. I don't even care what K is. 0 has to be less than K because K has to be a positive value. And sure enough, K is 2.5 times 10 to the third power. that 2.5 times 10 to the third power is much greater than 0. So this is going to move towards the right. And it follows our standard rules for that. If you ever had an instance where you had 0 on the bottom, which means you have all product, no reactants, obviously we call that undefined because we're dividing by 0, but that's obviously going to shift towards the left. Moving on to number 34. And this one, this is more of a conceptual problem. They have this following reaction which occurs when a burner on a gas stove is lit. So natural gas in your homes is usually methane gas. Methane gas is CH4, and when it combines with O2, it becomes combustible and lights. And you've all seen, I'm sure, a natural gas stove go on fire. And when that happens, we're producing CO2 gas and H2O gas. So that's water vapor, basically, and CO2 gas. So this is an equilibrium reaction. But is an equilibrium between these actually established under those conditions during a gas burner stove being lit? So how I like to look at this question is I like to draw a diagram. I always like drawing diagrams of things. So I'm going to draw, and I'm a terrible artist, so it's a diagram, not a picture. This is my depiction of a burner. Those gas burners, they kind of look like a little cylinder coming up, and they have a bunch of holes around the ring, either on the top or on the sides, usually with a little plate. So the fire goes up and then the plate spreads out the fire, either way. And what you end up with is propane coming out of those holes. I'm sorry, not propane, methane coming out of these holes. So methane's going to be kind of spewing out of there once you turn the gas on. And we're going to have methane gas coming up from there. And then O2, oxygen gas, is going to be floating around in the air all around it. So there's our reactants. Basically, we've set up our system where we have O2 gas, which is about, I want to say 40% of our atmosphere, but that might be wrong there. It's floating around in our atmosphere. Maybe it's like 15. I don't know. Doesn't matter. There's a lot of it in our atmosphere, enough for this reaction. So we actually have O2 in excess, we'll say, of what we need. Because it's in our atmosphere, it's in the air that we breathe. We are going to then ignite this. When we ignite that stove, we cause this reaction to start happening. So then, as we know, we get this flame of the reaction happening and releasing energy and heat coming out. And then it starts to produce methane. And I'm going to use green for methane. So methane gas, sorry, not methane, CO2 gas. So methane is my purple color. I should write this down. O2 is my blue color. I'm going to use green for CO2. So that should produce CO2 gas kind of coming out from all around there. Everywhere where that's combustion is happening, the product of that is CO2 gas forming in there. And it starts to kind of spread out as it goes throughout the atmosphere. As the wind picks it up, it disperses through the container that it's in. The container that it's in is either your house. Hopefully you have an open window, because otherwise eventually the CO2 will build up into a dangerous level, but it'll just spread throughout the atmosphere of Earth. And it'll also produce a water vapor, so about twice as much. Which will also start to disperse out from there. So the question is, will we reach an equilibrium at the state? So there's two things I look at. First of all, since the container that we're basically in is the entire planet, the CO2 gas and the water vapor is expanding out and eventually dispersing amongst all of the air on the planet and blowing in the wind and stuff like that, ending up in China eventually, or until it reacts with something else. We can't say that it's really a closed system on that regard, because we're actually removing that CO2, and that water vapor is being removed from the initial area of the reaction. It's dispersing throughout the environment. We're also continuously adding more gas to this situation. We're continuously pumping gas in here and out of there. So we're continuously rising the methane level in that general area, causing more and more of that reaction to happen. And we're removing the CO2 and the H2O gas from that immediate area, which drives that reaction towards the right-hand side, shifting it with Le Chatelier's principle. So since it's not really a closed system, we don't ever really get an equilibrium. All we really get is just this reaction continuously happening in a forward direction. It never really reaches enough concentration to go back in any significant amount. And when it does, it just combusts again. Again, because we're constantly removing this from the reaction, removing that from the reaction, and we're increasing that concentration. So since it's not a closed system, we don't really have that equilibrium state ever. And that's my terrible diagram. You can see I'm not an artist. Now it looks like a jumbled mess, but hopefully you followed the steps in which I took to diagram that out, and it made a little bit more sense. Well, oops. I was trying to get some of my arrows out. That looks a little bit more like a burner. Anyways, moving on. On 36, they want us to suggest 4 ways in which the concentration of hydrazine, which is N2H4, could be increased in an equilibrium described by the following reaction. So I'm going to write that a little bit bigger. Get my colors back. That's N2 gas plus 2H2 gas is in equilibrium with N2H4 gas. And they give us the enthalpy. The change in enthalpy is equal to 95 kilojoules. And the magnitude of that change in enthalpy, I don't really care about in this equation, but I do care about the sign of it. The sign of that enthalpy will tell me kind of whether it's endothermic or exothermic. So if we remember, if I were to graph its energy level, in this case, something along the lines of that, and I were to kind of plot the difference here between those is my delta H. It's the energy level. Well, this is energy, and this is the reaction process, essentially going across the bottom. So the delta H is going to be the HF, or H of the products, minus H of the reactants. So that's HP minus HR, I'll say, is equal to delta H. So if the products is a greater energy than the reactants, which it is in this case, we can see that delta H is going to be a positive number. I'll say greater than 0. This means it's endothermic. So it's actually absorbed some of the energy from the reaction and stored it in the chemical energy of the molecule itself. And we can see that because N2 gas and H2 gas are elemental gases, right? So they should have really a delta H of 0, where N2H4 should be then a positive number. If we were to have a delta H which is less than 0, that's going to be exothermic, because the energy state of the product is lower than the energy state of the reactant. So when we do products minus reactants, we end up getting a negative number. So in this case, we're looking at an endothermic reaction. And the endothermic reaction, since it's absorbing energy, we can say, or I like to think of it as, essentially we have heat as a reactant. And this helps me kind of determine how this reaction is going to respond to a change in heat using Le Chatelier's principle. In this case, we want to, because could the increase is described by the following reaction? So we want to look at 4 ways, and that's one of the ways we're going to look at. So if we were to increase this heat here, we can see that the reaction is going to drive to the right. It's all going to shift to the right because we're increasing one of the reactants, in this case heat. We could also increase the concentration of H2 and increase the concentration of N2. All three of those things are all reactants, and if we were to increase the concentration or the amount of heat that's given, we can drive this reaction, this equilibrium, more to the right-hand side, producing more of that product. So I'll write that here. So I can say increase the concentration of N2, I can increase the concentration of H2, and I can increase the heat. Because all of those are reactants in this equilibrium. The other thing we can do is looking at the moles of the total moles of the reactants and the total moles of the products. We can see that there's 1 mole of N2 per 2 moles of H2 per 1 mole of N2H4 hydrazine. Heat doesn't really have a mole. So we're not going to count that. But we have basically 3 on this side and 1 over here. So there's less moles on the right-hand side, more moles on the left-hand side. Because of that, if we were to decrease the volume, if you remember that gas, no matter what the molecule is, takes up the same amount of space through the volume. When you decrease the volume of something, usually will increase the pressure, and by increasing that pressure, you encourage it to be less molecules, so it could reduce its pressure. So in this case, we have 3 molecules for every 1 molecule. So by decreasing the volume, you're going to shift it to the side that has less moles of gas, which is in this case the product side. So by decreasing that volume, we're going to also shift it to the right, which will give us more of that product. And I'll give you a bonus one. This is one that I think of, is to remove N2H4 gas from the system as it's being produced. How to do that, I don't know. I'll leave that up to someone who's more knowledgeable than I am to do that. But if you were to find a way to remove this from the system as it's produced, you break that equilibrium and you drive that reaction to completion. So all of your products, all your reactants are going to be used up to make that product because we no longer have that equilibrium state. So this breaks the equilibrium, but it does produce more of this hydrogen gas, which is what we're trying to do. Looking at number 38 now. How will an increase in temperature affect the following equilibria? And they also want to know, how will a decrease in volume of the reaction vessel affect each? So this goes back to part of what we talked about last time, but now we're looking at 4 different reactions, and they're giving us changes in enthalpy for each of them. So the first one is 2NH3 gas is in equilibrium with N2 gas plus 3H2 gas. And we're going to see it's a positive delta H, so we know this is endothermic. And because it's endothermic, we're going to have heat, just like we did before, as a reactant. So I'm going to slide this over and throw in heat here. Now I can talk about, well, what happens if that heat goes up? We increase the temperature. If I increase the temperature of this, we're driving it towards the product side, towards the right, because we have more reactants than we did, so we're going to end up with more products to balance that out. So I'll write, if temperature increases, it shifts right to the product side. So what about volume? If the volume decreases, is what they say. Well, if the volume's decreasing, we want to look at that mole-to-mole ratio, the moles of the products and the moles of the reactants. So the moles of the products, there's 1 and 3. So there's 4 total moles in the product side. Here we have 2 moles of the reactant side. So by decreasing the volume, we're going to shift to the left towards the side with less moles, especially because they're all gas. If it's a liquid or a solid, that doesn't apply anymore. But as long as it's a gas, the gas prefers to have less moles to fill that space because then there's less pressure involved. So for part B, we have N2 gas plus O2 gas is in an equilibrium with 2 NO gas. And here again, we're endothermic. So again, I'm going to add heat as a reactant. So as before, if the temperature goes up, we're going to drive that to the right. Again, heat's a reactant, so if it increases, we're driving it to the product side, creating more product to balance out the increase in reactants. The temperature increases, it shifts right. So if the volume decreases, in this case we have 1 mole of N2, 1 mole of O2, and 2 moles of NO, which means we have an equal number of mole-to-mole ratio in products and reactants. So decreasing the volume is not going to have any effect on the equilibrium. Because the amount of gas per volume is really going to be the same for all of those. Part C, that's 2O3 gas. It's in equilibrium with 3 O2 gas. In this case, it's exothermic, which means it's releasing energy as a product. So I would need to add plus heat on the product side. So now when I increase temperature, we can see, again, the heat goes up. This is going to shift back towards the reactant side because we're adding more of the product, which is going to slow down the reaction rate of the reactant side of it. So this is going to shift left. Really, it's going to increase the reaction rate of that reverse reaction because there's 2 different reaction rates in equilibrium. Both of those rates are the same. By increasing the heat on the product side, we shift everything back a little bit. We increase the rate of the backwards reaction, which causes that equilibrium state to be farther towards the left. If the volume were to decrease, volume decreases. Well, again, we have a 2 to 3 ratio. The volume decreasing favors the one with less moles. So in this case, it's going to shift left as well. There's 2 moles of O3 where there's only 3 moles of O2. Last one we have on this problem, part D. Let's see, that's calcium oxide, CaO, as a solid, plus CO2 gas is in equilibrium with calcium carbonate. CaCO3, which is a solid. And finally, it's exothermic, because that delta H is a negative sign. So, looking at this one, if it's exothermic, that means we're going to have heat as a product. If you have a reaction that can happen at room temperature and it's an exothermic reaction, you can feel the beaker of the reaction and it'll get warm. It'll be warmer than the outside air, warmer than the liquids, because it's radiating off this excess energy that it has. But if we were to increase that temperature of where the reaction's happening, the equilibrium state of it is going to shift back towards the reactant side, shift to the left. Now here, if we were to decrease the volume, so we have 1 mole of calcium oxide, 1 mole of CO2, and 1 mole of calcium carbonate. But some of these are solids. We have 2 solids here, the product and the reactant. So really, those solids are not going to be affected by a decrease in volume. If you had, salt in a little glass jar and you put it into a smaller glass jar, it doesn't care. But if you had gas, CO2 gas, in a balloon and you squeezed that balloon, the pressure is going to go up. So that's basically what's going to happen, is we are decreasing the volume. So we're really just decreasing the concentration of the CO2 gas. The amount of solid isn't really affected by that in any way, shape, or form. So the only thing that's going to change is we're not decreasing the concentration of CO2. We're actually increasing it, because that concentration will have the same number of moles, but the volume's gone down. So that's going to increase our concentration. By increasing that concentration, we're shifting this to the product side, to the right. I didn't write left up here. So if the temperature increases, since it's exothermic, we're shifting back to the reactant side to the left. If the volume decreases, we're actually increasing the concentration of CO2 gas, which is going to shift things to the right. Next one I'm going to do is number 40 here. So here, methanol can be prepared from a carbon monoxide and hydrogen at high temperature and pressure in the presence of a suitable catalyst. So they want us to write the expression for the equilibrium constant, Kc, for the reversible reaction. So they give you this reaction here. That's 2H2 gas plus CO gas is in equilibrium with ethanol, CH3OH. So to write out this equilibrium constant, that's Kc is going to be equal to the concentration of CH3OH, which is a gas, so it counts, divided by the concentration of CO times the concentration of H2. And H2 we have to square because it has that coefficient of 2. It's really H2 plus CO, so we have to multiply all those together. And that's going to be our basic equilibrium constant. So that's part A. Part B, C, D, E, and F is all talking about, well, what happens if I change something. So I'm going to go ahead and just write out this equation that they have here. 2H2 gas plus CO gas is in equilibrium with CH3OH gas. And we're going to see, based on this, it's going to be exothermic. So I'm going to go ahead and also add plus heat here. So now for part B, what will happen to the concentrations, all of them, at equilibrium if H2 gas is added? So we're increasing that H2 gas there. By increasing one of the reactants, we're going to shift everything to the right. Right? So this is going to shift right. For part C, I'm going to change to green. Let's use green. See what will happen when the concentrations, or to the concentrations H2CO and CH3OH at equilibrium if carbon monoxide is removed. So here we're decreasing the concentration of carbon monoxide. Well, that's going to shift to the products, or to the reactant side, to the left. Because now that we have less concentration of that, the rate of the forward reaction is going to decrease, and the rate of the back reaction is going to stay the same. So it's going to continue to adjust until it finds that new equilibrium point, which is going to be lower to the left. So this is going to shift left. Let's go part D. What will happen to these concentrations if CH3OH, that methanol, is added? So now we're increasing methanol. Well, if we're increasing one of the concentrations of products, we're going to shift back this way. We're going to increase that reaction rate of the back reaction, shifting to the left-hand side. So the next one is the temperature of the system is increased. So we're increasing this heat. Well, that's the same idea. We're increasing one of the products. Heat, in this case, is a product because it's exothermic. So we're shifting it backwards to the left side. Now, finally, part D. Oh, sorry. Ooh, I'm going backwards. Part F. What will happen to the concentrations at equilibrium if more catalyst is added? Well, if you add more catalyst to this, it doesn't really change the concentrations of anything that's there. So all the concentrations are going to stay the same. In that case, there's really going to be no change. Got another one here for you. This is a different reaction. Same idea as what we're doing before. For part A, we want to write the expression for the equilibrium constant for this reversible reaction. Again, we're going to have Kc is equal to the concentration of the products. We start with the CO, H2. We're going to divide that by the concentration of the reactants. But we don't count solids in that concentration, nor do we count liquids. We're just looking at gases or aqueous solutions. So those are the only things we really want to pay attention to. So in this case, just H2O concentration at the bottom. And everything has a stoichiometric ratio of 1 to 1 to 1. So we're done there. Again, writing out this reaction, C of a solid plus H2O, should be a bigger 0. That's better, which is a gas in this case, which is important because otherwise it wouldn't be part of my constant. Just CO gas plus H2 gas. So for part B, what will happen when the concentration of each of the reactants and products at equilibrium or where H2O is removed? So the concentration of H2O is being reduced. That's going to shift everything to the left-hand side. We're removing that product. I'm sorry, we're removing that reactant. Therefore, the forward reaction rate is going to drop, which is going to shift that equilibrium state. So this is going to shift left. For part C, what color did I use? Well, here, I screwed up. I did part C first. Oh no. So this is part C. I did C first. Let's go back and do part B. Okay. I'm going to blame the heat on that one. B. If more carbon is added. Well, if more carbon is added, we have more solid going up, but that doesn't exactly change the reaction rate, because the reaction rate's not dependent on carbon. It's only really dependent on this H2 gas. So in this case, I would say there's no reaction, there's no change. So let's put in purple for part D. And here we're looking at the change in CO2 being added. We're increasing the concentration of CO2, which is going to change that equilibrium constant. It's going to shift it to the left. The back reaction rate is going to become faster, and we are going to end up with a shift left. Finally, for part E, here we are increasing the temperature of the system. And then, you know, one thing I didn't mention, this is an endothermic reaction. We have a positive delta H. And since we have a positive delta H, heat is going to be a reactant. So if we increase that heat, we're going to drive this reaction to the right. So those are some really good examples of Le Chatelier's principle, and it's really a good idea to see just kind of the general behavior, the touchy-feely way that these reactions at equilibrium are going to behave when you increase a little bit of this or decrease a little bit of that, and you can use that to control things to a certain degree. We're going to move on a little bit to calculating the concentration levels at equilibrium now. So number 65 here says calculate the number of moles that HI that are at equilibrium with 1.25 moles of H2 and 1.25 moles of I2 in a 5.00 liter flask at 448 degrees Celsius. So that temperature is important because this constant changes for different temperatures. So they're giving us the constant at that temperature. So we can use what we got there. But if this were to change temperatures, we're going to have a different constant. So as we saw, the heat affects whether or not it shifts to the left or to the right, which inevitably will change that equilibrium constant. So in this case, we can see that if we write out our equilibrium constant equation, that's going to be equal to the concentration of HI squared divided by the concentration of H2 times the concentration of I2. And we can then use the information they gave us to solve for the concentrations of H2 and I2. We know that there's 1.25 moles of H2 and there's 1.25 moles of I2. So there's an equal amount of those because we have the same, they're both in that same volume of flask. So I can say that the concentration of H2 is equal to the concentration of I2, which is equal to 1.25 moles divided by 5.00 liters. If we do the math on this, 1.25 divided by 5, we get 0.25. 0.25 molar. So now that we have that, we can utilize that. Because what we need to do is solve for this concentration up at the top, right? And using that, we can then determine the number of moles. So we can rearrange this equilibrium constant equation to solve for that HI. So if I do a little bit of math, I'm going to rewrite this first. It's equal to concentration of HI squared divided by the concentration of H2 times the concentration of I2. I'm going to multiply each side by those concentrations on the denominator. H2 I2. These here are going to cancel out. That'll leave me with concentration of H2 I2 times Kc is equal to the concentration of Hi squared, which means all I have to do is take the square root. I can solve for the concentration of Hi. Now we have what these concentrations are. We solve for those up here on the left. So we can just plug those in now. We also have the Kc value of 50.2 at that temperature. So plugging those values in, I have the square root of 0.25 times 0.25 times this concentration, which is 50.2. So if I do that math, I take the square root of 0.25 times 0.25 times 50.2, and I'm getting 1.77. That'll be in molar. And unit-wise, this was in molar, this is in molar. We're then taking the square root of molar squared, which is equal to molar. So the units do match, which is something I always do try to check. So now we have the molarity of Hi. So what we need to do now is use that to determine moles. So we know we had a 5-liter flask. So since this is equal to 1.77 moles per liter, we can then take that 1.77 mole per liter, we multiply it times 5.00 liters. We can see the units cancel out to give us moles, and that 1.771298,958, that number times 5 gives us 8.86. mole of Hi. So that's how we can determine the, that shouldn't be molar, this should be moles. Moles of Hi. And that is what they're asking for. So that's a good way to use equilibrium constants to solve for the concentrations you'll have at equilibrium, which is an important step in chemistry, because you want to know, well, after this reaction is done, how many moles am I going to have? Or sometimes you know how many moles you need to have. You have to back it up to see how much of that reactant you need to start with. To take that one step further, this next problem, we want to find out the concentrations of the products and reactants, PCl5, PCl3, and Cl2, in this equilibrium mixture, which is produced by the decomposition of pure PCl5. That the concentration of PCl5 that we have is 2.0 molar. So this is telling us this is what we're starting with. We want to know what are the concentrations at that equilibrium point, and they give us the equilibrium constant for this. So for this type of problem, we use what's called a Rice table or ICE table. I've heard it called both. It really has to do with this wonderful acronym going down here. And this stands for reaction, initial, change, and equilibrium concentration. And if I make this into a little chart, and then I can write the reaction at the top. So that's going to be PCl5 is in equilibrium with PCl3 plus Cl2. And for the initial, we're writing that initial concentration. We don't know what is the concentration at the initial state. Well, initially, all we have is the reactant, right? And we have 2.00 molar. of that. The products, we haven't created any products yet. We have nothing there. It's a pure sample to begin with. So we start out with nothing. Then we say, well, what's changing? Looking at the stoichiometric ratios, we have a 1 to 1 to 1 ratio going on here. So because of that, for every mole that PCl5 loses, we're going to add 1 mole of PCl3, and we're going to add 1 mole of Cl2. And I'm saying X because X is that change in concentration that we don't know. Now they're all in the same container in this mixture, so the volumes are going to be the same in these. So for every mole that gets added for a loss of PCl5, we're going to gain 1 mole of PCl3 and gain 1 mole of Cl2. If these stoichiometric ratios were different, if we had a 2 here, for every 1 mole we lost of PCl5, we would gain a 2x instead. That's an ugly 2x. It would be plus 2x if that were the case. So you can see how we can utilize this depending on what those ratios are. But in this case, it's just a 1, so we're going to leave it like that. So then the equilibrium concentration, well, that's what we really want to solve for, we can write as an expression. So it's really just the summation of the upper two columns. I'll even write a little line there. So this is going to be 2.00 minus x. Just taking the top one, and we're going to add the bottom one. Since it's negative, it's 2 minus x. 0 plus x is just x. 0 plus x is just x. And then we have basically our concentrations are going to be at those expressions. So now we need to be able to plug that into an equation and solve for it. That equation that we're going to use is the equilibrium constant equation. So which is equal to the concentration of Cl2 times the concentration of PCl3 divided by the concentration PCl5. Now, since each of these represent one of those, we can do some substitution. Then we can say that Kc is equal then to x, which is the concentration of Cl2, times x, concentration of PCl3, divided by 2.00 minus x, which is the concentration of PCl5. And Kc, we know, is this value here. We'll use that in a little bit and do some substitution in there. I want to rearrange a few things first. So now what we really want to do is solve for x, because we know what this variable is here. So the only unknown we have in there is x. And we have one equation there. We should be able to solve for that. So a little bit of rearranging, and we can figure that out. We see that x is being multiplied by x, which means it's going to be a quadratic equation. So we're going to rearrange it as so. First, I'm going to multiply each side by 2.00 minus x. 2.00 minus x. And that's really to get rid of this denominator. So then I can distribute this Kc here into that binomial, giving myself 2.0, I'm just going to say 2 Kc, we'll worry about sig figs at the end, minus Kc times x is equal to, what's left on the right hand side is just x squared. And to get this into a quadratic equation so we can solve it, if we remember, we want this to be like x squared, or I should say ax squared plus bx plus c is equal to 0. And then we can plug it into our quadratic formula. So to get it into that state, we need to add kcx to both sides. And we need to subtract 2 kc from both sides. So that'll be 0. So we'll end up with 0 is equal to x squared plus kcx minus 2 kc. So in this case, if I were to relate this, a is equal to 1, b is equal to kc, and C is equal to negative 2 kc. And now we can plug it into our quadratic equation. So that's one that if you don't have memorized, write it on your cheat sheet, have it handy, because it's a really useful thing to be able to solve in these equations. Sometimes you have a fancy calculator which will solve it for you, and that's fine as far as I'm concerned, as long as you know how to get to that point, set it up, get the answer from it, and interpret what that answer means. So in this case, we can plug in these variables over here on the right into our equation. So that equation is x is equal to negative b plus or minus the square root of b squared minus 4ac all divided by 2a. That's your quadratic equation. And we're substituting in a, b, and c for those. When we do that, we can see we end up with negative kc plus or minus the square root of kc squared minus 4 times 1 times negative 2 kc all divided by 2 times 1. And that's going to equal x. There's a lot there. We have that plus or minus in there, which in this case we'll find out it doesn't really matter, because once we do a little bit of substitution, we'll see how that gets simpler. So if I substitute in now my value of kc, which is this 0.021 up at the top, we can see that that's going to be a negative 0.0211 plus or minus the square root of, I'm going to make that a little longer, 0.0211 squared minus 4, and then it's minus 4 times a negative, so I'm going to make that a plus 4 times 2 kc. I should put in that kc, so it's really times 2 times 0.0211. And I'm going to divide that whole thing by 2. So let's start out. I'm going to do this in sections just to make it a little easier to follow, especially since you have that plus or minus in there still. We need to make sure that we can utilize that properly. So 0.0211 squared. Yes, first I want to take the square root. So I'm just going to do at first this part here, just everything under that square root and the square root itself. So I'm going to take the square root of 0.0211 squared. I'm going to add that to 4 times 2 times 0.0211. So now I can rewrite this, if I can get my pen. That's going to equal so far negative 0.0211 plus or minus this number here, which is going to be 0.4114 all divided by 2. So right here is where we can see this is a negative number. If we were to subtract this number from it, we would end up with a negative k value. And we can't ever have a negative k value. That should always be positive. So in fact, this always has to be the plus version of that. So now we can see if I take negative 0.0211 and I add to it this last value I got from the square root, and then I can divide that number by 2, this is going to equal 0.195, which is going to be the concentration, so it'll be in molar. This is equal to then the concentrations of PCl3 and Cl2, because that's equal to X. And Cl2. So we're almost done with this. They want us to find all 3 concentrations. We found just the concentrations of the products, not what the concentration of the reactant is at equilibrium. To do that, we have to plug in this equation. So we now have solved for x. We have to subtract x from 2. So 2.00 minus 0.195 This gives me 2.00 minus this number here. It's going to give me 1.80. 1.80. That's going to be in molar, which is equal to the concentration of PCl5 at equilibrium. So now, with this and this, we were able to solve what those concentrations are at equilibrium just by utilizing the equation for the reaction and that equilibrium constant and the initial state of the reactant, how much reactant we had. So you can go in a lab and do this. You have this much reactant, you know what the equilibrium constant is. There's tables, you can look that stuff up, and you can then determine, well, how much of these concentrations am I going to have? And we use that based on this Rice table. And again, it's reaction, which is just the reaction equation, the initial concentration, so whatever you're given initially. Usually the products start out with nothing, but sometimes there's a little bit of those products in there already, but just put it on the Rice table and take account to it, and the math kind of figures everything else for you. The change is what's changing. Usually the reactants are going down by X or some multiple of it. The products are going up by similar amounts, either X or some multiple of it. And then we can add those top two rows together to get the equilibrium concentrations. And then it's just plugging all those values into this equilibrium concentration equation and solving for that X value. If you're lucky, sometimes if X ends up being a really small number, we can negate that part of it and simplify things a lot. But when all else fails, just do the quadratic equation, which again, if you can't do it by hand, it's a good thing to learn. But your calculator can usually do it for you. Just learning how to do that, especially to double check the work you might do by hand, is really useful. That's all I have for you today. Thank you for tuning in to this video. I'm sorry if you tried to tune in to the live stream and I was late. I had internet troubles and I got onto it as soon as I could. We're going to continue this on into Chemistry 223, so look for an announcement on D2L about that, and I will see you guys later. Enjoy.